Question 4a. A parallel circuit is connected to a 1.10 times 10 to the power of 2 volts DC supply and a switch as shown. One branch of the circuit has a 22.4 ohm resistor, R1, and an uncharged capacitor, C, in series. The other branch has only a 27.5 ohm resistor, R2. Sketch clearly labeled lines/curves on the axis on the right to show how the voltage across each component, R1, R2, and capacitor, C, will change when the switch is closed at t equals 0 seconds. Explain why the voltage across each component changes in this way. The graph will look something like this. R2 is connected in parallel, so it will have a constant 110 volts. The capacitor is initially uncharged, so it will start at 0 volts. As the capacitor charges, its voltage will increase to a maximum of 110 volts. However, the increasingly charged plates will increasingly repel the oncoming charges, thus it will gradually slow the rate of increase. R1 is in series with the capacitor. This means that it must start at 110V such that the capacitor and R1 voltages add up to 110 volts. As the voltage across the capacitor increases, the voltage across R1 will decrease accordingly. Question 4b. The capacitor is removed from the circuit and replaced with a non-ideal inductor. The non-ideal inductor has both inductance, L, and internal resistance, R. At t equals 0 seconds, the switch is closed. The voltage across each component, R1, R2, and L, is measured for 3.00S and plotted on a graph on the facing page. Using physics principles, explain why each of 3 lines on the graph has the shape it does. R2 is connected in parallel, so it will have a constant 110 volts. Initially, when the switch is closed, there is a high rate of change of current, which will lead to a high induced back EMF from the inductor. This will be equal to the voltage supplied by the source. After time, the current will start to reach a steady state. This means that the back EMF induced will decrease and will eventually end up with a 10-volt drop due to internal resistance. As R1 is in series with the inductor, the voltages across R1 and the inductor must always add to 110 volt. Since the voltage across the inductor starts at 110 volts, the voltage across R1 must start at 0 volts, such that the voltage across the branch will add up to 110 volts. R1 will eventually have a voltage of 100 volts, such that it adds up to 110 volts with the inductor's internal resistance. Question 4c. Use information from the graph to estimate the time at which the current through R1 and the current through R2 are equal. V equals IR, so I equals V over R. The resistance of R2 is 27.5 ohms, and the voltage across R2 is 110 volts. The current through R2's branch is 4 amps. R1 has a resistance of 22.4 ohms. The voltage across R1 when 4 amps of current flows through it is 89.6 volts. When the voltage across R1 is 89.6 volts, the time is roughly 1.15 seconds. Question 4d. Using information from the graph, calculate the value of the inductance, L, and internal resistance, R, of the non-ideal inductor. The final steady current through R1, and therefore the inductor is 4.46 amps. When current has reached steady state, voltage across inductor's internal resistance equals 10 volts. Substituting our numbers in, we get the internal resistance of the inductor is 2.24 ohms. Time constant equals inductance over resistance. Rearranging this gives inductance equals resistance times time constant. The time constant is the time taken for a 63% change. Looking at the graph, the time taken for a 63% change is about 0.5 seconds. Substituting our numbers in, we get the inductance equals 12.32 Henry.